In this video, we're going to be learning two easy but still very important definitions on limits. The first one we're going to study are one-sided limits. The definition for one-sided limit says we have a function f, and we say that the limit of f as x approaches x0 from the right is L if for every epsilon we have that there exists a delta such that f of x minus L in absolute value is smaller to epsilon if x is between x0 and x0 plus delta. So what this would be is that 0 is smaller to x minus x0 and this is smaller to delta. Notice the difference between this expression and the one we had with the original definition of a limit. Analogous to this, we have the definition of the one-sided limit as x approaches x0 from the left. And this limit will be L if, again, we have that for every epsilon greater than 0, there exists a delta such that the absolute value of f minus L is smaller to epsilon if x0 minus delta is smaller to x, and this is smaller to x0. So now x minus x0 is negative, and it's also greater to minus delta. The notation we're going to be using for the limit to the right is that the limit when x approaches x0 from the right of f of x is L, and from the left it is the limit when x approaches x0 from the left, that is from the negative side of f of x is equal to L. Let's see what this definition means graphically. Let's first draw the axis, and let's say that this point here is L. So let's first start with the limit from the right. The plot for something like this would be if this point here is x0, then our function coming from the values that are greater to x0 has to have limit L. And then the function can do anything like this. But from the left, it doesn't have to necessarily happen this. We can have this limit here. So if we call this limit here L2, then we have two things for this function f. We have that the limit when x tends to x0 from the right, that is in this direction, of f is if we come like this, we know that the final value is near L. But now the limit coming from the left has this value as a limit, which is L2. So the limit when x tends to x0 from the left of f of x is equal to L2. And now we can think about another function like this. This function, when we look at the limit like this, that is from the left of x0, it has limit L. So the limit when x tends to x0 of this new f of x, the pink one, is L. And the limit when x tends to x0 from the right, from the positives, the last one was from the left, of f of x, is this value here. Let's call it L3. So that is the definition of a one-sided limit. And as usual, with a new definition comes a new proposition. This proposition says that we have a function f defined in an open set, except perhaps in a point x0 in AV. This is because we don't care about the value of our function in x0. In this previous example, we didn't care if the function was defined in L, in L2 or in L3. We just cared how the function was behaving when we took values to the right of x0 or to the left of x0. but we never talked about the value in x0. So we have that the following assertions are equivalent: that the limit when x tends to x0 of our function f is L, and that the limits when x tends to x0 from the right and from the left of f of x are equal to this number L. Graphically, it's pretty evident, because if we draw the axis and say we have a point x0, if this point here is L, now let's do a function with limits from x to x0 from the left will look something like this, with this limit equal to L. But then the limit from the right, according to this, is equal, so it has to do something maybe like this. And if we have this, it's pretty obvious for us to have that the limit when x tends to x0 of f is L, which makes total sense because it's what's happening here. Now the proof for this is super easy, and so I'm going to leave it as an exercise. It's just using the definition of a limit and the definition of limits to the right and to the left. And now something I want you to notice is that it says that the following assertions are equivalent. So when we have this, it means we have to prove that 1 implies 2, and also that 2 implies 1. So this is another way of defining the limit of a function in x0, saying just that the one-sided limits are equal. Let's do a few exercises. The first one is going to be very graphical, and it says that the limit when x tends to x0 from the right of the function square root of x is equal to 0. And we're going to visualize this one in a graphical way. We know what the plot of square root of x looks. It's something like this. And so when we think about the limit, here, x0 was equal to 0. We're looking at the limit to the right. That means we have to get closer to 0 in this direction. Looking at the values of x for values of x greater to 0. And when we do this, we notice we get points that are closer and closer to 0. So we know this is true. Now let's look at this other example. Let's have a look at the limit when x tends to 2 from the left of the function absolute value of x minus 2 divided by x minus 2. So the first thing we have to notice is that we're getting closer to 2 from the left. That means that x goes to 2 from the left implies that x minus 2 is smaller to 0. And this is because we have to remember the definition of the limit. We said that x minus x0 was smaller to 0. So if x minus 2 is smaller to 0, that means that the absolute value of x minus 2 is equal to minus x minus 2. This is just using the definition of the absolute value. And so we can try and calculate this limit. We know now what the absolute value of x minus 2 is. And it is minus x minus 2. So now we can cancel those two terms. And notice that we can do this because x is different to 2. We're not taking the value x equal to 2. In that case, this would be undefined. We're just getting close to 2, but not exactly getting to it. So then with this, we are calculating the limit when x tends to 2 from the left of minus 1. And we've seen in previous videos that the limit of a constant is the constant itself. Now let's try and calculate the same limit, but when x tends to 2 from the right. In this case, we're taking values greater to 2. So x tends to 2 to the right implies that x minus 2 is greater to 0, again using the definition we saw at the beginning of the video. So then this implies that the absolute value of x minus 2 is actually x minus 2. So we can try again, calculate the limit. We know the value for the absolute value, that is x minus 2. And we can cancel these two terms out because of the same reason we gave before. And so we're calculating the limit of 1. And this limit is just 1. So then with these two last examples, we have that the limit when x tends to 2 from the left of x minus 2 in absolute value divided by x minus 2 is equal to minus 1. And the limit when x tends to 2 from the right of x minus 2 divided by x minus 2 is equal to 1. So we have two different limits for the one-sided limits. So using the proposition, if these two things are equivalent, then what happens is when this is not valid, then this one is not valid. So then we can say that the limit when x tends to 2 of the function does not exist. And this is pretty much all there is to know about one-sided limits, so we can move on to the next topic, which is infinite limits. The definition of an infinite limit is we have a function f, and we say that the limit of f when x tends to x0 is plus infinite if for every positive m there exists a delta such that when we take values of x between x0 minus delta and x0 plus delta, then the values of our function are greater to this number m. Graphically, if we have at this point x0, then our function is doing something like this. And so when I take a number m, let's say this one, I can always find a delta, which would be this number. This interval would be the x0 plus delta and x0 minus delta, such that when our function takes values between these numbers, then it is greater to m. If I can change my number m for another, and for every value of m I can find this new delta, then the limit of our function is infinite. And as before, we have an analogous definition for minus infinite. And what changes here is that for every m that is smaller to 0, there exists a delta, such that if x minus x0 is smaller to delta, then f of x is smaller to m. And the typical drawing for this kind of situation would be like this. If this is x0, then our function would be doing something like this. But there are some other cases. For example, if we have the axis and x0 and our function does something like this, then it's a mix between the two cases, because we have that the limit when x tends to x0 from the right is minus infinite, because when we get in this direction our function is going negative, and we have that the limit when x tends to x0 from the left of f is infinite, because when we're going in this direction, our function is going up. So for this kind of cases, we define the limit when x tends to x0 of f of x is equal to infinite without any sign. And the definition for this is that for every m greater to 0, there exists a delta such that if x minus x0 is smaller to delta, then the absolute value of our function is greater to m, because then the absolute value of our function here would be the positive one would stay like as it is, and the negative one would be like this. And so we're back at having this case. So let's finish this video with an example. We want to prove that the limit when x tends to 0 of 1 over x to the power 3 plus x is equal to infinite. We have to prove something for every m. So let's start with saying let m be a number greater to 0. We want to see that the absolute value of our function is greater to m. And saying this is equal to saying that x to the power 3 plus x in absolute value is smaller to 1 over m, or m to the minus 1. So what we're going to do is something we have done in previous videos. We take a delta prime equal to 1. Then if x minus x0, which is 0, equals to the absolute value of x, is smaller to 1, this means that minus 1 is smaller to x and smaller to 1. Then what happens is that x squared plus 1 is between 0 and 2. And so we can say that the absolute value of x squared plus 1 is smaller to 2. But now the thing we want to bound is x to the power 3 plus x. So let's write it. X to the power 3 plus x in absolute value. We can take common factor x, and we have x squared plus 1. This is the reason why I did all this. So now the absolute value of our product, we have absolute value of x times the absolute value of x squared plus 1. Because of this bound we have here, we can bound this term and have that this is smaller to 2 times the absolute value of x. This 2 comes again from this bound. So when bounding x to the power 3 plus x, we can just bound this expression 2 times the absolute value of x, and then this one would be already bounded. So let's try and make this smaller to m to the minus 1. And now we can take and isolate here x, and we have that the absolute value of x is smaller to 1 over 2m from here. So what we're gonna do is we just take delta equal to the minimum value. Notice that this x is actually x minus x0 because x0 was 0. So we take a delta equal to the minimum between 1 and 1 over 2m. So if the absolute value of x minus 0 is smaller to delta, then we can start to prove if x to the power 3 plus x is actually bounded by 1 over m. This is equal to the absolute value of x times the absolute value of x squared plus 1. And now we can make this smaller because we have to consider that delta is the minimum between 1 and another number, and x is smaller to delta, so the absolute value of x is smaller to 1. And so we have the bound we got before, 2 times the absolute value of x, because this is smaller to 2. And now this, because also absolute value of x is smaller to 1 over 2m, then this is smaller to 2 times 1 over 2m. And we can cancel these two out and get that this is 1 over m. So we took a number m that was greater to 0, and we were able to find a delta such that if x minus x0 was smaller to this delta, then x to the power 3 plus x was smaller to 1 over m. This whole thing implies that 1 over the absolute value of x to the power 3 plus x is greater to m. And then the limit when x tends to x0 of 1 over x to the power 3 plus x is equal to infinite, which is exactly what we were trying to prove.